Revisited.
Thank you, Dave. So in the previous presentations, a number of people have talked about the burst altitude, the height of burst. And I've been talking about that for some time. And I think we are not necessarily using consistent language. And this came up last year when Dave organized a workshop at NASA Ames on Tunguska. And people kept talking about height of burst. And since the 2017 PDC, which was also, or sorry, the 2007 PDC, which was here in Washington, I've been claiming that there's an effective height of burst that's lower than the altitude of peak energy deposition. And I made that argument that year. And I've kind of been sticking to my story for about a decade, but our discussion at that workshop made me question that and want to revisit it. So that's what this presentation is about. So I actually went back to try to remember what I had said in published papers and abstracts and so forth. And I actually really wasn't using the term effective height of burst. At that conference 12 years ago, I used apparent height of burst, and I was talking about what it appeared to be like from directly beneath. I was running 2D axially symmetric simulations. And so my claim was it was significantly lower than the point of maximum energy deposition, but I was using a trick. I had been up when I started running these simulations. I was adjusting the strength of the asteroid I was modeling to try to get it to explode at a particular altitude, and it was just impossible. And it had to do with resolution issues, primarily because I was not running on big machines at that time and I didn't have the resolution. So I came up with this trick of sourcing energy into the asteroid, basically just setting it off like a bomb with some fraction of its kinetic energy. And I chose 40%. So 40% is almost 50%. So if you set it off at some altitude, that almost by definition is the burst height. And as I will show you, I ran simulations and it always went down much more deeply, and most of the shock wave source seemed to be at a much lower altitude. So this is that was my title slide 12 years ago. And so 60% was kinetic energy, 40% was internal energy that was sourced. And I looked at this as kind of a bounding simulation, because when you think about it, the argument is that its momentum carries it downward, but there's actually less momentum than there would be in a real event. So if it were a real event and you weren't sourcing that energy, but it was deposited at that altitude, it would be moving down even faster, that amount of mass, to conserve momentum. So I actually did 6 cases. I'm only going to show the 5 megaton ones because those are fairly consistent with what I think was the Tunguska impact. And so here's just one of 6 2D simulations that I showed at that conference 12 years ago. And it's not running. So those who were here 12 years ago saw it. You've seen much better ones already at this conference. Sarah had beautiful ones. So these are snapshots. And what I did to define that apparent height of burst was I said, okay, think of the source of the blast wave as being what it appears to be from beneath. And it's the first thing that arrives. And it's roughly spherical in shape. And so the magenta circle that I have on all 3 of these were 3 different trigger heights, or prescribed burst heights by that 40%, which was 2 megaton explosion, 20, 15, and 10 kilometers above the surface. But it continued on downwards significantly. And so then the apparent burst heights were much lower, and I state that in this slide. And this also appeared in my Journal of Impact Engineering, the proceedings of the Hypervelocity Impact Symposium, which was also that year. So now I'm going to do the same thing, but I updated it to be only 2% sourcing of energy. And that way I really develop what is a more realistic energy deposition curve. And I hope this one runs. There we go, good. So this is very similar to what I showed 12 years ago. And you can see, it does burst. And this is very different from the model that Lorian showed. This is pure hydrodynamics. But it does continue to lose its kinetic energy. That kinetic energy goes into kinetic energy, internal energy of the atmosphere, goes to kinetic energy of the atmosphere, internal energy of the atmosphere, and internal energy of the asteroid material itself as it vaporizes and is entrained into the wake and is ejected outward. So anything that's not kinetic energy, I define as going into energy deposition, which I think is consistent with others' definitions as well. This is the 15-kilometer trigger height. And again, you see instabilities. You see a lot of vortices forming, and that is a mechanism by which the energy deposition is not necessarily smooth. And I think if I ran these at higher resolution, you'd see this type of vorticity and turbulence at even a much smaller scale, and that may affect the energy deposition as well. And here's a 10-kilometer trigger altitude. And so if I do the same thing I did 12 years ago, I can nest these spheres and kind of define the apparent burst height from directly beneath, but that's not the only energy that gets coupled to the ground. So one thing I did this time that I didn't do 12 years ago is CTH and other hydrocodes allow you to do all this diagnostic instrumentation. You can put in Lagrangian tracers, and you can output global variables, which I did this time. And so I can actually calculate an energy deposition curve, and see if I can, I think the light is a little weak. So there are a lot of curves on here. It's a very busy graph. The bright red one is kinetic energy. So the derivative of that kinetic energy is what I define as the energy deposition curve. And you can see this nice monomodal energy deposition curve at the bottom, the black curve, which has one peak to it. And so if you wanted to just approximate the effects on the ground, which is what we're interested in for risk assessment, you could just set off the entire 5 megatons at that point and compare that to what the hydrocode would predict you would see on the ground. I also plotted momentum at the tracer because the momentum is global, that's output, but I also put the tracer in so I could see what that momentum applies to. The tracer is at the center of mass and tends to follow the asteroid right up until the very end. And I also calculated the mass associated with that tracer. So you're losing momentum, but you're maintaining velocity. It still remains at very high velocity. So even at the point of maximum energy deposition, it's got very high downward velocity, and that energy continues to be advected downwards. I'm just going to show these very quickly just to show that the energy deposition curve determined this way can be very complex. And it is also chaotic. It turns out if you change the resolution, if you change the precise details of how you start the calculation, you get a different curve. It's in general follows the same pattern and the same range of energy deposition, but it can be very different. And here's the one for the lower altitude of burst. And I've got arrows there defining the various different heights of burst. Okay, this is the Gladstone and Dolan curve. This is the damage on the ground, and you can see the peak. This is basically scaled in the distance of for a standardized 1 kiloton explosion that you can use for scaling. And there's actually, depending on the damage on the ground you're interested in, there are different optimal heights of burst. And so I use this curve as an alternative way of calculating the damage on the ground and this is for much lower than the 250 megatons that kind of describe the limit of application of glass, stone, and dolomite. So here are comparisons. Now mine are circular because this is a vertical, axisymmetric. And the upper one is the static source glass, stone, and dolomite. And you can see they're actually bigger. But if you look at the high damage area, the area of the high damage part, it's actually bigger for the vertical asteroid airburst that actually uses the full, entire energy deposition curve. So for the glass, stone, and dolomite approximation, you get more broken glass. And for the full energy deposition, you get more casualties. So then it becomes a question of how you do your risk assessment. Very quickly, I'll go through these last ones. As you know, I'm very interested in the beta Taurid possibility for Tunguska. So I also ran a couple of these at entering at a 32-degree entry angle. And these are the curves associated with that. And now we've got this non-circular energy deposition curve. This is the comparison with glass, stone, and dolomite. And actually, I didn't go through and measure the areas, but it's extremely close. And here's another one. And this one, actually, the glass, stone, and dolomite is worse. So here are my conclusions. It is actually a useful concept, but we need to be more careful about how we apply it. And I look forward to collaborating with the ATAP group as well as with Sarah, who's also doing very relevant work along these lines. Thank you.
Thank you, Mark. Are there questions or comments?
I think, yeah, I think you get a better answer if you put in a full energy deposition curve. But I'm not sure it matters to within a factor of 2. And as Al Harris and others have said in astronomy, a factor of 2, is pretty good. But, there's also, as Al pointed out, there's a factor of 2 uncertainty in the populations, probably at least. And if you start getting a factor of 2 and a factor here and a factor of 2 there, it starts to add up. And, for risk assessment, you want to minimize uncertainties.
Okay, thank you, Mark.